Well, let's go on to some maybe a little bit harder concepts. I left everybody yesterday with the thought experiment. So now that we have this signal that we all are experts on that are in this wire that we're feeding into a computer, how do you generate an image out of it? Anybody have some thoughts?
Yes, Sheila does.
So evidently Sheila's the expert here. Sheila?
God. You explained it so nicely, Sheila.
No, I didn't. No. Well, I think that we have to determine how to localize the signal that we're getting. So we have to create, and especially like in a person, whether it's from the head to the toe or left to right, anterior to posterior. So I think that you have to localize it by doing like slice different encoding of sequences. So maybe slice encoding, phase encoding, frequency encoding, so that you can create like a voxel or have a voxel, and for each voxel determine an image. I guess, make an image.
So do you want to go through that process or do you want me to?
I'll let you do that. That was my extent of it.
Well, back in the late 1970s when Damadian first came up with the concept and tried to apply it in biologic tissues, magnetic resonance, the first device that he developed was one called field focusing, where he basically took all the areas of the body except for one small little voxel. He created magnetic field variation so that only a small voxel in the body was at the Lamar frequency. So then when he did the experiment, only the nuclei in that small voxel would actually resonate and give a signal. And then he would move the voxel. So you can imagine how long it takes to do a study like that, where you'd have to do a separate sequence for every voxel in the body. It could take days to get a simple 2D image. But that was the first commercially available MR scanner was a field focus type scanner, which the name Phonar. But then very early on, people used more sophisticated ways to more efficiently determine the source of where the signal is coming from so that they could do a map of signal intensity versus spatial location within the body, which is when you display that is what we call an image. So here's a typical scanner. This was one of the first images obtained. This was back in on a 0.5 Tesla scanner, 5 millimeter thick image. There's a date somewhere. 1983. This was one of the first scans that GE did and when they were trying to develop their first Sigma scanner. And you can see it's a very nice image of the pituitary. So this was really quite a hit in the very early days. This is before they actually had a commercially available machine. See how this is very different from the MECT scans that we're dealing with in those days, which were 10 millimeter thick images with very poor contrast and very poor spatial resolution. CT's come a long way since then also, but that was a major advance. It got people interested. This was about a year or two later, and we could see a nice big syrinx in this cervical spine, a T1 weighted sagittal image. Again, we can see that the image quality has come a long way since those days. But even then, on the very first rudimentary scanners, and this is a 1.5, one of the first 1.5 Tesla images, you can see that we're actually seeing a lot of things. We'll talk about, see this black line here, and there's a white line on this. There's a black line on the inferior part of the vertebral body and a white line on the superior end plate. Why would the end plates be different in signal intensity? Michael?
Correctly, I think it's chemical shift artifact.
Okay. That's chemical shift artifacts. So we'll talk about what that is. And you can tell from this that the frequency encoding is up and down. Okay. Now, if we talk about basic pulse sequences, and this is kind of the basic one that really started this whole thing. And we're going to talk about 2D Fourier transform spin echo images to begin with, kind of the basics. And with this experiment, what we have is a 90-degree pulse followed after a time period of tau with a 180-degree pulse. and a time period of 2 tau, which is TE, we end up with an echo here. And we'll explain how that happens later in more detail. Notice that there are 3 gradients that are applied, and you need 3 gradients because we have to localize the signal in 3-dimensional space. One is called a slice encoded gradient, one is called a phase encoded gradient, and the other is a frequency gradient, readout gradient, which is this one right here. And as we'll see in a minute, we'll talk about what the slice encoded gradient does. That'll be the first one we'll talk about. Then we'll talk about the frequency encoded gradient, and then we'll talk about phase encoding. Notice that these gradients are placed on the object at different times. If you place them on at the same time, it's actually the equivalent of one gradient that's in an oblique direction. So if you're doing 3-dimensional imaging, you have to apply the gradients at different times. And we'll talk about that. So what we're trying to do is from the electrical signal in a single wire, we're trying to determine where in 3-dimensional space it's coming from. So some areas may be darker, some areas may be dark, some areas may be light. If we can determine where the signal is coming from, then we can differentiate tissues based upon the strength of the signal. We'll talk first about localizing the signal, and then we'll talk about why signal is different in different tissues. So we need 3 linear gradients. Okay, so let's start out here. Susie, what is a magnetic field gradient?
What is a magnetic field gradient?
I'm not quite sure.
Okay, I use the term magnetic field gradient. What did I mean when I use that
I
term?
wonder if you meant like when you place a coil on somebody, their X, Y, and Z fields? No?
Okay, no. So, now, what's a gradient mean? Just what does the term gradient mean?
I thought the term gradient had to do with the X, Y, and Z fields.
Okay. Well, a gradient just means that you've got a change in whatever you're talking about. It changes over space. So by magnetic field gradients that we're going to talk about here, we have the main magnetic field, which let's just say it's 1.5 T. And when I put in a magnetic field gradient, I'm going to make one part of the body lower in magnetic field and another part higher in magnetic field. So let's start out first, let's say a magnetic field gradient along the z-axis. The z-axis, we have a solenoid superconducting magnet, the z-axis is along the solenoid going from head to foot when they're in the scanner. And if I put a magnetic field gradient, then I'll make the feet in a slightly lower magnetic field than the head. So if we're at 1.5 T, I might make the feet at 1.49998. And I'd make the head at 1.5002. And I'd like it to be a linear difference. So right in the middle, it'll be at 1.5000. And it'll be, if I go 5 centimeters to the right, it'll go up X amount. 5 centimeters toward the head, it'll go up X amount. If I go 10 centimeters above the head, it'll go up 2X, all the way up to the head. And similarly, if I go down 5 centimeters, it'll go down X. If I go down 10 centimeters lower in the body, it'll go down 2 times X, linearly all the way to the foot. So that would be a linear gradient. Frequency encoded gradient will be similar, a linear gradient. And if we're doing, say, an axial sequence through the body, that could be right to left. So the left side of the body would be at a low magnetic field. The right side of the body would be at a higher magnetic field. Again, these are small variations with respect to the main magnetic field, B0. But as we'll see in a minute, they're very important. And then the phase encoded gradient would be in the Y direction. So we've covered all 3 directions. And the phase encoded gradient is the one that gives everybody the most difficulty. And we'll get to that later. We know what voxels are. So this is just an example of a Z gradient. So here we're talking about the head being at a higher magnetic field, the feet being at a lower magnetic field, and this would be a linear magnetic field gradient. So the head's at 1.502 Tesla, the feet are around 1.4998 Tesla. So that would be a magnetic field gradient, okay? So that means that the nuclei precessing in the feet, Sean, are they precessing at a higher or a lower Lamar frequency than the waist?
They should be precessing at a, I guess, a lower frequency.
Yeah, they'd be precessing at a lower frequency. The brain would be precessing at a higher frequency.
Higher frequency.
Okay. Now, Yuri, if I then put in a radio frequency pulse in a very narrow frequency range, in this particular case, just a little bit under 64 megahertz, then what we can see happens here is that if the RF pulse is only in this narrow band here, that means that it will not be at a frequency that will affect the foot protons, right? It'll only be at a frequency that will affect the nuclei in the brain. So by putting on a gradient like this and putting in a narrow band of transmit RF, what part of the body will the nuclei be resonating in? What will it look like?
I mean, you will be selecting the slice in the head, or yeah, up top.
Okay.
So
it'd be basically an axial slice through the brain,
right.
So
Right.
the reason we call this the slice encoding gradient is if you do 2D Fourier transform imaging, this gradient actually selects the slice that we're going to work with. Okay? Now let me go back for a minute. If we go back to this pulse diagram, so what happens is I put a Z gradient on whenever I give the 90-degree pulse. I put a Z gradient on whenever I give the 180-degree pulse. And that means that only the nuclei in that axial slice through the brain will see the 90 and 180-degree pulses, right? That means the nuclei in the rest of the body won't be playing. So all the signal we get in the wire will only come from the nuclei that are in that plane through the brain. Okay? So we've selected a single slice through the body. That's why it's called the slice encoded gradient. Any questions? Okay. So that's slice encoding. And then now, Sheila, how are we going to make let's say I want a thin slice. How can I make the slice thinner and how can I make it thicker?
To make the slice thickness, change the number of voxels. I don't know. I'm not sure.
No, I'm saying how do you make the voxels thicker?
How do you make them thicker?
So look at the diagram. Tell me how.
I mean, make it, I guess.
Look, what determines how thick this slice is?
The ratio, I guess, of the gradient to the resonance frequency. I mean, it's a point on the graph, so
Let
you
me
have.
ask you this. What if I made the bandwidth twice as wide here? What would that do to the slice thickness here?
It would be bigger.
Okay, if I made this space bigger, that would go from there down to here. Then that slice up here would go from there to there. So if I double the bandwidth of the transmit pulse, I'll double the thickness of the slice. If I narrow the bandwidth of the transmit pulse, I'll narrow the thickness of the slice. Can you see that? So one way to make the slice thickness narrower would be to make the transmit radio frequency pulse narrower in bandwidth. Okay? Michael, what's the other way I could do it?
think if you had a larger gradient,
Okay, so if the gradient were steeper, so that it came down like this, then would that make it narrower or wider? Okay, so here's just an example where the gradient is kind of the standard gradient. If I have a thick bandwidth, I get a thick cut. If I have a narrow bandwidth, I have a narrow cut. Now here's a case where we have the regular bandwidth, the same bandwidth on both of them, but this gradient is steeper than that gradient. And if it's steeper, it leads to a thinner cut, thinner slice. So you can determine the slice width, the thickness of the slice, by either changing the bandwidth of the transmit pulse or steepen the gradients. And depending upon the way the scanner and the electronics are set up, there's an optimal way to do it. And the manufacturer usually doesn't give you the choice. They do it for whatever, however way they think is most optimal. So you usually will type in the slice thickness you want on the console, and the computer will determine how it's going to change these two parameters to give you the best image. Okay? So any questions about that? So this is the slice encoding gradient. Okay, that's one direction. Now let's go to the next one, which is the frequency encoded direction, which in our example is going to be right to left. Okay, now that's this readout gradient, which is primarily on when we receive the signal. Forget about these little blips. We can talk about them later if we want, but that's for some technical reasons. As far as the signal is concerned, uh, it's on while we're receiving the signal. It's off at all other times except when we're actually receiving the signal. And here's the signal. This just means that we're turning off the receiver at all times so that we don't get any noise into the system. We only turn the receiver on when we want to receive the echo, and then we shut it back off again. Okay? So we turn on the receiver, the analog to digital converter, when the echo comes. And at the time, along while we're turning on the receiver, we put the readout gradient, which let's just say is right to left here. Okay, so how is that going to help us right to left? Now, we can only do the slice encoded gradient in one direction. You can't do it in two directions, but using this particular technique anyway. So now we have to do frequency encoding. All right. Susie, do you know, can you tell us what frequency encoding is? Okay. Let's say we're how many people play musical instruments? Yuri, do you play?
No, sir.
No? Oh, okay. I don't really either. Though I futz with the guitar. Sean, do you play a musical instrument?
I used to, yeah.
Okay.
Clarinet.
Clear. Oh, all right, good. Well, let's just play like we're all harpists, okay? And so I have a harp set up here in the lecture room, and I'm going to take Michael and put him out in the hallway so that he can't see in. Okay, but I can leave the door open so he can hear me when I pluck a string. And I'm going to sit at one end of the harp, and Michael has perfect pitch, so he knows exactly what note is being plucked when I pluck it. And the thing is, I'm going to pluck one of these strings, and I'm going to ask Michael which string I'm plucking. So by telling me which strings, he's really telling me how far along the x-axis here on this harp I'm stretching my hand out to. So he's going to hear a frequency in his ears, and he's going to tell me how far my hand is being stretched along the x-axis. So we're encoding the position of my hand in a sound which is a specific frequency. So if I pluck a low note, Michael's going to tell me, well, I'm only stretching my hand 5 centimeters. If I pluck a high note, he's going to tell me you're 35 centimeters out when I pluck it with my finger. Okay? So now this is frequency encoding. By knowing the frequency of the sound, Michael can tell me exactly where my finger is in space. Right? Is that clear? How you do frequency encoding? Except we're not going to use sound, we're going to do electricity. So now the reason this is the case is that we have a gradient of sounds here. We have low pitched up here and we have high pitched far away. So when we put a gradient at the time that we have the readout, so what's happening is we've excited all these spins, they get out of phase, we give a 180-degree pulse, which we're going to talk how it does this later. That causes them to rephase at times 2 tau and we get a signal again. Now, what we're going to do is, at the time we do the 90 and 180-degree pulse, there's no gradient in the x-axis. So we're basically we're resonating all of the spins throughout the entire plane that we've selected through our slice selection gradient. But we're going to do a trick. When we receive the signal, we're going to put a gradient along the x-axis. Now, the nuclei are going to come back into phase, but remember, when they resonate, they have to resonate at the Lamar frequency that corresponds to the exact magnetic field that they're in. So even though we first stimulated them at 1.5 Tesla, when we put that gradient in the XY direction, the ones on the right are going to resonate at 1.4998 megahertz, and the ones on the left are going to resonate at 1.502 megahertz. So they'll resonate at different frequencies. So my left side would be like the little tiny end of the harp. My right side will be like the big fat end proximally. So they resonate at different frequencies. So the computer will receive that signal and it'll say, aha, this one's resonating at 1.4998 megahertz, therefore it must come from the tip of my left hand, or unless I have it backwards. And somebody else is resonating at 15.02, so that must be the tip of my right hand. They're at opposite sides, depending upon which side I make high and which side I make low. So now when we receive the signal, first we know that any signal we receive has to be in that axial plane through the brain, because only the nuclei that were selected by the slice selection gradient are going to resonate. And then when we put the magnetic field gradient at the time we receive the signal, any resonance that we receive at higher frequency is going to be on one side of the body, and the lower frequency is going to be on the opposite side of the body. So now we know which side of the body they come from. So we've localized the signal now in 2 planes, right? Any questions? Susie, any questions? Okay. Now let's just take a look at this. How does it look? So if we have a signal in our wire that comes around like this, we can see that that's a nice sine wave. And if we just have a kind of beaker of water there, and this is a sine wave, say on the left side of the body, it'll resonate at a frequency based upon that big on the left side of the body, which in this case is a low frequency. Now if we put another beaker of water, or if we shift that beaker of water to the right side of the body, it's going to be in a higher magnetic field, therefore it's going to resonate at a higher frequency, and we'll know that it's coming from the right side of the body, right? Now, if we have 2 beakers of water and we do them both at the same time, one will give us a low frequency, and in this case we have a big beaker at the low frequency side. One will give a high frequency, that's a smaller beaker. When you add the 2 together, we get a complex signal. This complex signal, if we knew how to read it properly, would tell us that there's a lot of water on the left side and a little water in a beaker on the right side. This is the signal that comes in from our wire. It's going to be a very complex signal, but somehow we're going to have to figure out how to separate that signal into each of its component frequencies to tell us where on the XY plane that signal is coming from. And that's what we'll talk about in a minute. That's what Fourier transforming does, and that's something that's very easy for a computer. That's a slam dunk for a computer. It's a little hard for humans to look at this and say that that's the sum of these 2 frequencies, but very easy for a computer. So here's just that water. Here's a beaker of water here, a bigger beaker of water there. If we have no gradients, we get a nice signal coming from both of them and a single peak, but we have no spatial uh, information. If we put a readout gradient on or a frequency encoded gradient on, where the bigger beaker is at a higher frequency, we end up with a very complex signal. But if we Fourier transform that, and the Fourier transform just takes a complex signal and divides it into the amount of signal in each frequency band, we get a little bit of frequency from this beaker and a lot of energy from that beaker. And if we know exactly what the gradient is, we can tell exactly where these two beakers are located. And that's the signal from the two of them. So this is how you get frequency encoded information. Any questions about that, Sean?
No, I'm good.
We good? Okay. Now I'm going to break just for a second because this is a good time to talk about chemical shift. Okay, Sean, what's type 1 chemical shift artifact?
I wasn't sure there was different types, but my understanding is that it's the way that the let's see how to explain it.
There's a type 1 and
It's
a type 2. Let's start
yeah,
with
well, I guess my understanding was that there's a slight difference between the resonance between like two different substances, like a fat and a water, because they're so different, and that the computer then just can't quite distinguish between which voxel the signal should go into it, so it kind of shifts it 1 or 2 pixels in one direction in frequency direction. That's the best I can explain
good.
it.
That's very good. Now the reason is that remember the computer assumes that everybody starts out resonating at the same frequency. And then if you put a magnetic field gradient on it, any shift from the basic frequency is going to be due to the gradient we put on. That's what the computer assumes. But if you remember, we talked last time that if you have water, which is a small molecule, has very few electrons binding it together, so it has very few shielding electrons, and therefore the protons in the hydrogen of the water molecule basically see the full magnetic field. But if we take fat, fat is a huge molecule. It has hundreds or thousands of electrons spinning around the hydrogen nuclei. And those many clouds of electrons shield the inside of the molecule, so the protons actually resonate at a lower frequency than the water molecules resonate at. And that's why we can get a spectrum like we talked about before. But the computer thinks that the fat nuclei should resonate at the same frequency as the water nuclei. But we know that they all resonate at a slightly lower frequency. Therefore, when the computer maps the source of that signal, it's going to map fat signal always at a lower field than water, and therefore it thinks it's actually shifted in the direction of the lower part of the magnetic field gradient. So if we have a magnetic field gradient where, let's just say, the left side of the body is high, the right side of the body is low, and if we have a beaker of a mixture of fat and water, the water image would be shifted slightly. The water image would not be shifted. The fat image would be shifted slightly to the right. So in a sense, they'll be kind of blurred. What this means in the lumbar spine is if we have the frequency encoded direction superior to inferior, which we often do in the spine, and we can talk about why we do that most of the time, what you would find is the fat within the marrow space of the vertebral bodies will be shifted in the lower frequency direction. The water tissue, which is primarily the discs, will not be shifted at all. So what you'll find is you'll have a black line on one side of the disc and a bright line on the other side of the disc. And I think we saw an example of that a few minutes ago, right? Let's go back and see if we can see that again in this old image. And that's what's happening here. We could see from this image right away that the frequency encoded direction is up and down along the z-axis. And we can see that the low frequency direction is above, the high frequency direction is down below, because we can see that the fat is shifted upward about 2 millimeters with respect to the water that's not shifted, that's in the disk space here. Okay? So by looking at this image, we know which direction is the frequency encoding, and we know which direction is the low uh, field direction and which direction is the high field direction. So in this case, the feet will be at a higher magnetic field than the brain. Okay? Any questions?
Dr. Cruz,
Yes.
I'm sorry. I'm confused. I thought frequency encoding direction was from right to left, or was
It was
the
right to the left in the first example, but in practice, which would be the, which is the, which direction, if this case is a sagittal image through the cervical spine, Yuri, which direction is the uh, slice encoded gradient in?
I thought it was from superior to inferior
That,
craniocaudate direction.
that's only if we do an axial slice. What
Uh,
direction is it in if we do a sagittal slice?
um, then it would be in
It has to be right to
coronal.
left. It has to be right to left because we're selecting, remember, the slice that we make has to be perpendicular to the slice encoded gradient. So if
Okay.
we do an axial slice, the slice encoded gradient has to be superior inferior. If we do a sagittal slice, the slice encoded gradient has to be right to left. If we do a coronal plane, it has to be anterior to posterior.
Okay.
So Yuri, what if I want to do a 45-degree angle? Uh, let's say that I want to do a an oblique coronal through the supraspinatus muscle and tendon.
Hmm.
Which direction would the slice encoded gradient be in then?
Um, it would be at 45 degrees to the
Yeah,
basically to the scapula, to the glenoid axis.
it would be oblique. It would be roughly a 45-degree angle with respect to the straight coronal plane. It would be kind of perpendicular to the face of the glenoid. So, so the bottom line is that if you're doing a 2D Fourier transform image, the first gradient that you put on is going to be in the slice encoded direction for the 90-degree pulse, and that gradient you put on in a direction that's going to be perpendicular to the slice that you're creating. So if you want an axial slice, it's in the up down direction. If you want a sagittal slice, it's going to be right to left. And if it's a coronal slice, it has to be anterior to posterior. Okay, so that would be your slice encoded gradient. Then your frequency encoded gradient has to be in one of the other two orthogonal directions, and then the phase encoded direction would be in the last orthogonal direction. Okay, is that clear?
Hmm. Yes, thank you.
Okay. So there's frequency. And okay, so let's talk about type 1 chemical shift artifact, which we just saw an example of in that sagittal T1 weighted image through the brain. That two tissues uh, have different shielding uh, electrons in their electron clouds, like water versus fat, then the nuclei in the large molecules will be resonating at a lower frequency. And then when you put on the frequency coded gradient, they will all be shifted toward the low frequency direction with respect to water. So So this is just an example. If you have a beaker of water, of a mixture of water and fat here, so that they're both in the same beaker, and you put on a very strong magnetic field gradient, you'll get a signal that just looked like the one we had before. And then when you actually create an image, you'll find that the fat and water would be separated if you have a strong enough gradient. But in reality, they're together, but you separate them just like in that sagittal image we had here. The fat and water, the fat and water are separated here. And we can see that there's an area where we have no signal because the fat's been moved superiorly. And here we have a very bright signal because the fat and water are now overlapping one another. Okay. So that's called type 1 chemical shift artifact. And here's just an example in the ankle. Let's see, Sheila, what direction is the frequency encoding direction here? And which side is the low field side and which side is the high field side?
Okay, so this is a sagittal image. So the frequency encoding, I think it's anterior to posterior. I think no. Okay.
Yes.
Uh,
Okay. So where do you see the black line and where do you see the bright lines?
I see the black line at the posterior. Yeah,
So here's
it's
a
at the
big, thick
inferior
black
aspect,
line
the tibia,
here. But the
posterior
subtongue
facet.
bone here you don't even see.
Also superior to inferior.
And there's a big black line there and a white line right along there. So what we're seeing is that the fat is being shifted upward.
Okay.
Okay? And see, so we have a big black line here. Here's water tissue down here. The fat's all shifted upward. So that means the frequency coded direction is superior to inferior. Which direction is the low field side of the gradient?
So the low field would be the inferior. No, I did opposite. Okay, superior, I guess.
Remember, water is essentially not chemical shifted. Fat has these big molecules with all these shielding electrons. So the fat nuclei are going to resonate at a lower frequency. So they're going to be shifted into the low frequency direction. And here, the fat is shifted upward with respect to the water tissues like articular cartilage here or muscle. So the low field direction is superiorly, the high field direction is inferiorly placed. Okay? So that's type 1 chemical shift artifact. This just shows blow up of that abnormality. There's a separation. There's you get overlap. Okay, now Michael, how does type 1 chemical shift vary with field strength?
So I guess you since you have a higher field strength magnet, it's going to change the precession frequencies of. So you have a larger difference between fat and water precession frequencies. So you have a larger artifact. No? That makes sense.
What happens is that the degree of shift, chemical shift, is directly proportional to the strength of the magnetic field. That is in frequency shift. So if you go from 1.5T to 3T, the actual separation in hertz between fat and water is double what it is at 1.5T. And the numbers are actually the following. At 1.5T, the difference in frequency between water and fat is 220 hertz. And that's just fixed. That's based upon the kind of fat and the amount of shielding that the shielding electrons does in the human body. If you go to 3T, that increases to 440 hertz shift. Now, if all of your frequency encoding is the same, then what you get is double the chemical shift artifact if you go from 1.5 to 3. Now, and then here's just an example. Here's the same individual, the same knee, first imaged in a 1.5T scanner, and then imaged in a 3T scanner. And you can see the degree of black line here is twice the thickness, just like we would guess from the physics. Here we can see a little bit of subchondral bone, here the tibia, and that's completely obliterated, and we'll see a white line around there where both fat and water overlap at 3T. So this shows that you double the chemical shift artifact when you go from 1.5 to 3T if everything else is the same. Now, what this is saying, and this is from Ray Kuo, a former fellow here who made this slide. Uh, what happens is that now there are two bandwidths that you have to know about in magnetic resonance. One is the transmit bandwidth that we've already talked about. And changing the transmit bandwidth changes the slice thickness of the slices, right? You'll probably not hear much about transmit bandwidth in the future. When you hear bandwidth in MR, what people almost always are talking about is the receiver bandwidth. And that's what you can change at the time of the scan.